And also, as I mentioned before, so your marks on the presentation is purely dependent on the peer review. All right, which means your marks on the presentation will be the average of the total mark on the form. So please give a fair mark on each of the group, and then we can get a fair mark for the presentations. All right, and I list 5 columns about the peer review. The first one is the quality of the project. You give the marks from 1 to 10, and the difficulty of the project you give as well. And then the presentation skills is from 1 to 10, and then you give a total mark. You give a total mark. The total mark should be some kind of like averaging, considering the previous 3 criteria. And then I will only consider the total marks, and then make the average on the total mark to make it as the marks on the presentation. So please be serious for this peer review, and also your mark is quite important. Your marking is quite important in the peer review. Also, I gave about the comments. So if you have any comments and constructive suggestions, so please put your comments there as well. And after all the presentations are done, so please send the review form back to me via email. All right, and please also put your name and your student ID in the form, and also in the name of the form. All right, and also you just need to peer review the other groups except your group. So you don't have to give marks to your own group. So that's why I put the name. I need you to put the name on it as well, because I will see if each student submit only one peer review form, and it's not peer reviewing in their own group. All right, and if I got some groups sent me the slides already. So if you haven't, you can send it to me anytime from now. And maybe if you don't want to send it during the presentation, then send it after the presentation. Send it to me as a. All right, so that's all the beginning. Then we can start our presentation. So the first one is, so I've just listed in the peer review form, and because I'd like to make the groups with same projects, and they will present together. Then you have a better comparison, or you have a better like feeling about which group is better, and then you can give a fair mark on that. All right. So and again, for each group, totally it will be less than 10 minutes. And with the first 8 minutes presentation and the coming 2 minutes for the question and answers. And please mute yourself during the presentation, and after the presentation. So you feel free to unmute yourself and ask questions. So anyone can just unmute yourself and ask questions. And when during the question and answer time, so each of the member from the group can answer the question. So just unmute yourself. All right, and then after 10 minutes, and we will move for the next one. All right, so that's welcome to the first one, which is group 5, and its project is about fetch robot following the past. All right, so group 5, please share your screen and start your presentation. Thank you.
Hello, testing.
Yeah, all good, all good.
Yep. All right. So, hey guys, our team consisting of Anthony, Tan, and myself had the project involving the fetch robot following the guider through an office environment. Um, so the scope of our project was to create an algorithm to allow the fetch robot to follow the path of the guider in front. So this meant we would be utilizing the sensors that are available to the fetch robot, which involves the RGB depth sensor and the 2D laser. The guider would have a special marker that would allow the robot to track it. And part of the scope was to also ensure the robot would not collide with either the guider or the objects in the environment. And to be able to complete these tasks, it would need to move forward, backwards, and rotate. And for an added safety feature, we also included into the scope the idea of maintaining a distance of 1 meter to the guider or any object. Yep, I'll take it to the next person.
Yep, so this is our flowchart of how the the flow of the program goes altogether. So the first part is it checks the camera. It checks both the RGB and the distance components of it. If that's okay, it'll continue on to check the LiDAR and check for obstacles around. Then it'll do the movement part and either rotate towards a frame or move towards or away from the target.
The RGB sensor is located at the top of the fetch robot, and it's got a resolution of around 640 by 480 pixels. And due to the fact that we have to run in a simulator, it'll capture noise-free images. I'll mention more on that later. And like Tan said, it's the first thing to run of the function that'll be, and that just runs in a loop, obviously. And the output image is fed into the feature detection algorithm. So to the left there, you can see the target matching, the feature matching, working with the robot rotation to center the target. What it will do is it will detect surf features and then match them and remove outlines. And then from that, it extracts the coordinates of the center point of the target, and it outputs that for later use to be able to center it. Initially, we had problems with the program stopping, even though due to not being enough inlier points found. But to fix this, all we did was we said only to filter for inliers if there's enough total matches. And we found that to get a better match in the simulator, due to the image being noise free, we could add noise to the reference image and the texture on the marker to create more detail to find. And also the reference image we found that needed to be downsampled to have about the same resolution and detail as the scene image from the camera, because we had problems with the reference image having too much detail, so it wasn't finding any matches.
Cool. Yep, so just like the RGB sensor, the depth sensor is also located in the head of the robot, and ultimately this was used to find the distance the robot is to the marker. So this relates back to that point in the scope of ensuring that 1 meter distance. This feature was easy to implement as each pixel value in the depth image actually displays a value in meters. So all we needed to do was feed the XY pixel coordinates collected from the tracking function to get the exact pixel the marker is in the image. From this, the distance was also used to determine the response of the system. So if the distance was more than 1 meter, it would move forward. less than 1 meter, it moved back. The next step in the workflow was checking the distance of the 2D laser scanner. So the laser scanner is located at the base of the robot and was used to detect the distance of objects within its 220-degree field of view. This would form the basis of our collision avoidance, as we can check distance the bot is from what is pretty much a large coverage. And yeah, so the collision avoidance was designed around the laser, so checking each laser index to see if any of them are within that 1 meter distance, which would cause the robot to stop to avoid collision. We would have hoped to have had a feature for reacting according to where the location of the object is, but as of right now, it simply stops and waits for the object to leave its collision range.
So for the movement, we used a PD controller to make sure that it goes to the right place. These plots are from when we were testing the rotational PID. So at first it would start oscillating quite a lot between the two extremes. And we managed to tune the PID to make the target reach the center of the frame in like an acceptable amount of time. So next up, the guider we used was modeled as a floating cube in Gazebo, and the marker was on the back face. It's effectively a turtle bot base used for the command side of things. And we've just hidden the turtlebot base and just used the cube for our simulation. If in reality, we'd probably use a person holding the marker instead, but for simulation, this was acceptable for our purposes. Yep.
So we have a 1-minute video of our run. So we'll let that play out. But essentially, some, I guess, points for our simulation. Since it was run in the simulation, this was about as much detail we could put into the environment without it performing really slowly. But at the end of the day, it's able to move and follow what I consider quite well. But yeah, while it's running, I guess we could go to some questions if anyone has any. Any questions?
Yep. So thanks for group 1. So group 5. So very very wonderful project. And just some questions. So one very quick one from me.
Yep.
So you said you've used LiDAR as well, right? So just confirming, is LiDAR for just collision avoidance, or it also used in the control of the distance as well?
For now, it was only used for collision.
Collision avoidance.
Yeah.
All right, cool. It's very good to have collision avoidance function in it as well. That is pretty great. Yeah. All right. So any other questions from others?
I have a question.
Yep.
It seemed like an interesting choice of a color marker.
Yes.
Using the triangle with the pattern. Was there a reason for that?
We just decided to use what we learned in class, the surf detection, features, extraction. So I guess we didn't really have a plan. We kind of just thought, we had a few iterations of the marker. So at first we just decided, let's try to create a unique marker that's wouldn't be found in an office environment. So we came up with this triangle, but that didn't offer much in terms of recognition. So we added a few asterisks, eventually to the point where we had to add a few noise, as Anthony mentioned. But yeah, we decided to take that route of creating our own marker to be recognized. Yeah.
Cool, thanks.
So, yep. Any other questions? All right, so if no, that's thanks the group 5 for their wonderful project. Thank you very much. Thank you. So please stop sharing the screen and then we move to the next one. All right, so the next is group 10 and their project is about fetch robot grasping. Yeah, feel free to start.
All right, good morning. I'd like to introduce our Fetch bartending robot. Thomas, Natalie, and I will be presenting on our achievements in this project. All right, you ready?
The goal of our project is to program the Fetch robot to act as an assistant bartender. This could be used to speed up production in a busy bar environment. This could also be implemented into high-end hotels, bars, and restaurants. The main inspiration for our idea was the robots used on cruise ships.
So the goals of our project was to make the bartender's job easier to handle more capacity of for drinks. So to do this, the robot is able to accept the customer's order, grab the ingredients for the beverage, place them onto the bar, and then put them back onto the shelf once they're done. Next, we'll show you a really quick demo about our robot. Here it's asked to make a gin and tonic, and so it finds the gin and it reaches for it, picks it up. And then next we're going to talk about White-tailed solutions. One of the issues that we had was lighting in Gazebo. We used AR tags, and that made it quite complicated to see the AR tags. If the lighting wasn't correct, it was also very slow to test because running Gazebo and the AR tag was quite difficult.
As seen in the project demo on the previous slide, the robot didn't quite manage to achieve the final set out goal as it dropped the bottle. This was due to a few factors. The first was that the Gazebo physics made the bottles difficult to move and rotate. This caused them to continually slip out of the bottle's gripper. The robot's gripper, sorry. In addition to this, when running the code in Gazebo, the bottle and the gripper would often collide with the surrounding shelf and bench. However, when we ran this in RViz with the same code, this did not occur. These problems could be partly attributed to either minor errors on our part in setting up the simulation environment or small incompatibilities within the Gazebo software. If circumstances allowed us to use the real-life Fetch robot, then these errors would likely have not occurred.
So I'll quickly take us through the ROS system. Our system used 4 main ROS layers as illustrated on the slide, where the flow of information is dictated by the arrows. First up, we have the drink menu, which takes a user input and publishes a custom ROS message with the drink name as a string and ingredients as a string name. Up next, we have Vision, which is subscribed to the drink menu and the Fetch camera, and it matches the drink ingredients array to AR codes in the Fetch camera. It publishes a geometry message with a pose array. Then we have Integration, which is the middleman program. It's a buffer for issuing commands to the gripper, and it's subscribed to Vision, and it calls custom services in the grasping package. Okay, the grasping package advertises 3 custom services: moving from the shelf to the bar, moving from the bar to the shelf, and a generic pick and place service. You might be wondering why there is 2 services for moving from the bar to the shelf and vice versa. And the reason for that is to do with the angles at which the gripper has to grab the bottle and the passer has to follow to place it on the bench. So the services accept the current and target pose and return a success fail indicator. And that's fed back into the integration code. And together, the integration and grasping code work together in parallel to ensure the information is passed back and forth until all the bottles are moved from the shelf to the bar and then back again. And this ensures the integration package always knows where the bottles are. So now we'll go through the individual packages used in our project. First up, we have simulation. So the simulation just for, for the simulation environment, we chose Gazebo. I just followed a rough Gazebo guide for setting up the environment. It's designed to emulate a real life bar with shelving for alcohol, bar surfaces, and it's even complete with a human bartender.
We also simulated the bottles. We had to use a custom model in SketchUp that we made in SketchUp. We used real life bourbon bottle measurements to have accuracy for it, which also meant we were able to import AR codes and real labels for the bottles. We tried to use models from Gazebo, but they were too hard to import and too hard to modify for AR tags. We have 4 types of alcohol: gin, vodka, vermouth, and Campari, which totals 5 types of drink.
So as mentioned, we have 5 types of drinks. First up, we have gin and tonic. Then we have vodka lemonade, vodka martini, gin martini, which both use 2 ingredients, and then Negroni. We also have a surprise me option, which picks a random drink for you. So the system knows the ingredients for the drinks, and then it uses slots and button callbacks to trigger a ROS publish whenever a button is pressed. The GUI was made with Qt Creator.
So as I stated before, for our vision, we use AR tags. This video is just one of them being detected as an example. The reason we chose AR tags was because it gave us the pose and the rotation of the bottle, which was important so you could know that it was the correct way. One of the biggest issues was lighting in Gazebo, as we said. It was inconsistent and it was hard to reproduce. It was also very slow to test as running Gazebo at the same time.
The aim of the grasping package was to move the Fetch Robot Gripper to a specified bottle coordinate while simultaneously avoiding the surrounding obstacles. As seen in the video, we can see the robot pick and placing a bottle off a shelf and placing it on the bar bench in RViz. This movement was controlled using the MoveIt software package. The bottle objects are defined based on their known size and coordinate positions provided by the Vision package. The arm is then able to plan a path and move to the bottle to pick it up. Modifications had to be made to the code so that MoveIt was able to pick up the bottles. This was because the bottles were also viewed as collision objects, meaning that MoveIt did not think it was possible to find a path without collisions. This was fixed by stopping the gripper just before the desired position and then moving it the remaining distance along a preset vector. These 2 images show the difference between the Gazebo simulated bar environment and the RViz environment. The RViz environment, we defined all of the collision objects from the real environment in MoveIt, and these are all of the collision objects shown here in green. By defining these objects, the Fetch robot is not allowed to go, is not able to, or it plans around the green objects. This avoids any collisions between the Fetch robot arm and its surroundings.
So as Tom mentioned, grasping in Gazebo, grasping RViz worked really well, but grasping Gazebo was a little bit different. And after a lot of work, it mostly worked. In Gazebo, the robot struggled to rotate the bottles after picking them up. As we alluded to earlier, this was due to incorrectly configured bottle physics. Some other challenges we faced were with the gripper. So when we set the gripper to close completely around the bottles, it would fail because it would violate the MoveIt tolerances. And if we set the bottle gripper to close to the bottle diameter, the bottle would slip out because it's not grabbing with enough force. So we probably needed to edit the controller tolerances a little bit. Yeah. Finally, this brings us on to integration. You've already seen how grasping and vision works. Integration is the middleman program between them. It's solely responsible for ensuring the bottles get from the shelf to the bar and back again. It takes the coordinates of the ingredients from the vision topic and calls a custom grasping service. It won't try and place an ingredient back on the shelf that wasn't successfully moved to the bar service, and it moves all the bottles required to make a drink to the bar so that the bartender can make the drink. It makes the most practical sense as opposed to moving one bottle at a time. After all the bottles are on the bar service and the drink has been made, it will move them back in the same order to the shelf again. All right, so that brings us to the end of our presentation. Are there any questions?
Thank you. Thank you very much. So one very quick question. I mean, it's a very good idea to use IR marks that to identify different. Wait a minute, someone's getting it. To identify different different kinds of alcohols, right? Then you do have to like do the pattern recognition with different shapes. But my question is, if you, I mean, suppose you're still using IR markers, but you're using different different shapes of the bottles, and can this grasping still work?
So we didn't actually end up using different shapes. I suppose it probably would have still been able to grip things, because I guess that was the reason we chose AR markers, because we could put the AR marker on any type of bottle. So if you put, you could put it on a bourbon bottle, put it on a gin bottle or a vodka bottle. We weren't able to test that though in our environment. Does that answer your question?
Yeah, cool, thanks. So any other questions? Any other questions? All right, so if no, let's thank Group 10 again. So thanks a lot for the presentation and the project. Thank you very much. And then let's move to the next one. Yeah, the next group is Group 12. The next group is Group 12, which is also working on the FetchWrap graphic. So feel free to start.
Okay. Hello, we are Augustine, Max, and Samuel. Our assignment focused on the Fetch Robot grasping task, with the specific goal of using the Fetch Robot to scan an environment detecting red, blue, and green blocks, then stacking those blocks into a single tower. This simulation was done within the gazebo environment, which needed to be set up for appropriate positioning, background, and lighting conditions for our operation. This video shows a fast-forwarded proceeding of the finished project. Our operation is split into several sections of code interacting with each other. We have a direct line of program flow via MATLAB, which interacts with the ROS camera detection to extrapolate data, which then sends messages to our Python code. Our Python code consists of a while loop constantly subscribing to these MATLAB prompts, and then using these prompts to manipulate the arm joints, gripping state, and camera movement of the Fetch Robot. Completion of individual movements are updated to MATLAB from Python in order to properly sequence through. Yep.
The program accounts for different configurations of blocks being present. So here you can see that there's no blue block present. And so what it does, it will detect the block, identify that there's no blue block, identify a green block, and then it'll go and pick and place the green block above the red block. So how do we detect the blocks? Well, first you had to calibrate the cameras. Initially, we did this using a similar way to tutorial 2, where we use a camera calibration toolbox to get these focal length and principal points. But later we realized there's a ROS topic that does that. Now, because this is a simulation, this is the ROS topic gives the actual focal length and principal point. But for a real camera with real manufacturing defects, we would have used the focal length and principal point from a calibration. So we attempted to detect the blocks in a bunch of ways. Firstly, Harris corner detection. And here you can see it's got 4 corners, but it missed the front 2 corners. Sometimes it would, in different orientations at different times, it would detect different numbers of corners. So it wasn't very reliable. We tried using Surf and Orb to compare an image to a standard image, but that that only ever detect 2 points as a maximum, sometimes 1 or no points, which isn't enough. We tried using edge detection with both these methods, and that didn't work either, because blocks don't have enough good features to perform reliable feature detection. So we ended up detecting the blocks by looking for clusters of blue, red, or green in the image. So here you can see the blue block and a big cluster of blue is found here. Then we found the center of that blue, you can see there, and that's our UV image coordinates. Now to convert that into the camera coordinate frame, we use general camera projection. So this matrix here comes from the camera calibration. This UV coordinates is from the image, and this Z, we plugged the UV coordinates into the depth image and added half the depth of the block to get the Z value. And that gives us the X, Y, and the camera coordinate frame. But we need that in the base coordinate frame. So there needs to be a rotation and translation. Now Ross has this transformation tree. And so down here is our camera coordinate frame, and it's got all the details embedded in it to get to the base link up the top. Now the orientation of the blocks was determined using the depth image. So here's that center point of the block, and you can find the edges of each of the block there. And then we found the depth at each point of the corners, and the X value, similar to before, of each of those corners on the image. And that gives a triangle there, which you can see here. Then we perform simple trigonometry to get the rotation.
Okay, for the arm movement, Fetch robot has 15 degrees of freedom, but in this project, we use only 7 arm joints and the solid joint for control the movement of robot arm. And we use another joint, is the gripper joint and head tool joint. Sam will give you more detail about this later. And after we know the pose, that means the position of the orientation of the block given from the MATLAB, then we need to calculate the joint configuration. That means the joint angle for the rotate of the arm. And the method we use is inverse kinematics. And the thing we need to know is how can we send the pose from MATLAB into Fetch Gazebo? The answer is ROS interface. ROS is mean robot operating system. It found maybe in nearly 10 years ago, and they can provide some services such as interface with sensor. As you can see, Matt use this service to catch the data, the data image from a camera and send it back into MATLAB. And another service is communicate with the other nodes at the same time. So that's why we can use ROS client and service to control the Fetch robot from MATLAB. But after we use that, we figure out this is not a good way. We have another way is Move It. Move It is the package that includes the Fetch Gazebo. Then you can use Move It to control the robot arm easy. And we just need to publish the post from MATLAB into Move It and subscribe the message which represent the motion finish or not. And after that, we can use that to make our flowchart and solve our problem. And Move It can detect the collision for us too.
Initially, we tried to use the grasping functionality provided by Move It. However, the number of required inputs, publishers, and subscribers we would have needed to properly implement this was quite large, while the standard gripper action server enabled by the Fetch robot was simpler by comparison. It was decided that while Move It was great for simplifying the arm manipulation, it needlessly complicated the gripping manipulation specifically for our project scope. The gripper will trigger via this breakdown as seen in the flowchart on the left. MATLAB will publish a message to topic grip check, to which a Python class will receive, which then triggers a grip function. This grip function is what directly sends an order to the gripper actions server. This order requires a goal state and maximum effort in newtons, and once that maximum effort has been reached, i.e. the block has been gripped, the Python function is informed, which breaks the function. This then updates finally the grip check topic to MATLAB, allowing it to continue its sequential operation. This flowchart depicts the transfer of data very similar to the arm movement, except instead of the ROS gripper action server, that would be where information would be moved to Move It, which would then continue its operation. The core of sending an order to an action server is also used to tilt the head camera down to get a full view of the blocks. Due to the scope of our project, we assumed a height and distance of the table, meaning the camera just needed to look down to a specific point. By putting this order at the start of the Python code before MATLAB had initialized interaction, we didn't require any direct communication to or from MATLAB in triggering this, or its completion. The head tilt action could have been designed with an almost identical program flow to the gripper function from the slide before, but because of the scope of the project, we decided the simplest and most effective design would be preferable. Next slide. Overall, we were successful in achieving our aim of designing a system which scanned the simulated environment, detecting the colored blocks and manipulating arm movements in order to stack the blocks into a tower. Does anyone have any questions?
Thank you for the presentation and a wonderful job. I might have two questions, very quick ones. One is, it's pretty good to consider the pose of the block, right? And then you can adjust gripper to pick it up. So do you have some experiments to test about what kind of like angle it can handle for the grasping? That's the first question. The second question is, do you consider the collision avoidance for the arm or for the end effector when doing the grasping? Thank you.
All right, so I'll probably take the question about the angle. So we have we did some testing at different angles, and so I guess we didn't find any problems, but I can perceive a problem occurring if it was at a 45-degree angle. So at a 45-degree angle, that red point is actually right on that corner there. It would actually detect this edge and that edge as the corners of the block. So it should work for any point as long as that red point is not right on the corner there, or a pixel or two away from the corner, because then it can track to the edge. Is that clear, Liang?
Yeah, that's clear. That's pretty clear. I mean, you don't have to consider like too much angles, and it will not be like perfectly 45 degrees, right?
Yes, as long as it's not perfectly 45 degrees.
Cool. And second.
Yeah, for the collision avoidance, we didn't manage to get the time to implement adding the blocks to the collision avoidance. Instead, we made sure that part of the code would have an appropriate approach angle where it would aim for, it would take the pose of the block and aim a little bit above it first, and then see, as you can see there, it goes a little bit above the red block, then down. So this is just to stop the gripper from interfering with the block as it approaches. During demo stages, there would sometimes be problems where it would hit a block that it wasn't aiming for. And in order to get more reliable interactions between these blocks, we would definitely need to add take the block pose and known parameters of the block and use those to add into the collision avoidance for the move it functionality.
Yeah, sure. Thank you. That's really good as well. Sure. Any other questions from other people? Yep.
I was just curious with gripping. Did you tell it to close the whole way, or how did you go about that?
Using just the functionality within ROS, we gave it a certain force in newtons, and it said before, once it reaches that force, it would send the message back and say this operation is done, and then go back up into the MATLAB flow. There are a couple very specific cases where, similar to the problem with a 45-degree angle, if it was a very wide angle of approach, then it would sometimes grasp the block and sort of reach that highest amount of newtons before it properly gripped it. But that was only a problem before we properly implemented the orientation approach of the blocks. So after that was fixed, that was no longer an issue.
Thanks.
So,
Yep. So any other questions? Any other questions? All right. So if no, let's thanks Group 12 again for their great job and presentation. All right. Thanks a lot. Thanks a lot. And then we can move to the next one. The next one is Group 3, and their project is about the turtlebot following a straight line. So feel free to share your screen and start.
Hello. 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 Can you guys hear me? Okay, cool. All right. So we have the Turtlebot following a blue square. For us, we did acquire the Turtlebot to do the project. So our project breakdown is basically to detect the color of the object and the shape of the object and then go towards the object. And in the meantime, we implemented obstacle avoidance in there as well. So the task breakdown for the project was, I was responsible for the initialization of the Turtlebot.
Sorry to interrupt. So you can display, you can display the slides.
Sorry, is it not showing?
No, put it in slideshow mode, Sanji.
Slideshow, yeah.
Sorry, okay. All right. So for the task breakdown, as I've mentioned, I was responsible for the LiDAR and basically acquisition and installation of the Turtlebot. And then Taha was responsible for the color detection and Cariel was responsible for the shape detection. This was our setup, environment setup, and we had the real Turtlebot as well to implement our codes. Yeah, for the setup, we basically had 4 objects, the red triangle, the green square, and there was a blue circle as well, which you guys cannot see. Those were used for as noise. So the Turtlebot was, the process the Turtlebot is supposed to follow is that it's supposed to rotate 90 degrees every time to check if the object in front of it is the target object. If it is the target object, then it's going to go towards it and stop like 10 centimeters away from the object, and then it's going to initiate a obstacle avoidance. It's going to initiate the obstacle avoidance algorithm so that it can move around the object and just go sideways. So that's basically a bit of information on the LiDAR that we had to use. That was that already came in with the Turtlebot. For the obstacle avoidance, I used the vector field histogram control method, as it had the target direction, the steering direction, and the distance limits as well. So we have a video for the obstacle avoidance here. Okay. Is the video playing on the screen?
No.
Okay. It's basically the Turtlebot implementing the obstacle avoidance algorithm, and then returning back to the slides. These are the graphs that I got for the VFH controller. You can see that the purple line is the target direction, and then the green dotted lines are the steering direction. So the blue bit that you can see, if the blue bit is in front of the Turtlebot, then it's basically gonna choose another feasible direction to move away from that obstacle and find a free space to go forward. Okay, so I'm gonna give it to Hope to explain the rest.
Yeah, so the Raspberry Pi camera that we used was the Model V2. It had a high quality of 8 megapixels, and it was capable of 3280 times 2464 pixel static images. So we had to use ROS to transmit the data from the Pi camera into MATLAB in order to process it. And for this sensor, we needed it to detect the color of the object as well as the shape of the object. The next slide. Yeah, Taha will explain this part.
All right, so the Pi camera was used for the color detection and calibration initially. So first we take the image with the camera, and then we want to transfer the image, receive the image from the ROS version and convert it into a MATLAB workable version. And then using a few lines of code, we can get the pixel information of the shade of the color that we're detecting. Once we're done with that, once we have the information, we can set the thresholding values, which is essentially the calibration stage. And after the calibration is done, when we run the algorithm, what it should do is take an image, convert the image to the three component colors, red, green, and blue. And then it takes the red, green, and blue colors, and then we put the filter for the red shade, blue, and the green shades. And once that's done, we get the images in forms of blobs, because they're not going to be perfect regular shaped objects. So we we go with the blobs, and we get the three masks of the blobs. And once we have the blobs, we get the area values. And this area value is important because we're gonna use this area to compare it with the size that so if the size of the area is too little, it's not gonna see it. It's gonna come out as a blank image. So if we use the LiDAR to come close to the object, like for a certain distance, and like once we view the image, if the object is the right one that we're looking for, which is a blue square, it's gonna go towards the object. And yeah, that's the algorithm behind the color detection. Over here, we have some screenshots. So this is a red triangle. And if you look at the shaded section, we have the RGB, capital RGB values. And it shows 0 if it is present, because I use a code that's called isEmpty, and it checks if the area is empty. And if it's empty, it returns 1. If it's not empty, it returns 0. So if it's 0, that means that color is present. And if you look at the shape, we get the right shape. In this case, it's a triangle. In the next few images, next few slides, you'll see it detects the correct, shapes. With the, yeah, and you can also see, you can again like compare it with the RGB values, and yeah. So the next section is the object detection, which will be taken on by Hope again.
Yep, so for object detection, in order for the for MATLAB to process for the data from the Pi camera, obviously we had to subscribe to the Raspberry Pi Cam node of the Turtlebot through ROS on Ubuntu. So in order to use object detection, we required the output from the color detection, which was the grayscale image that you saw before. Those blobs correspond to the color mask that we chose for whatever color that we were trying to look for. And then so we used region props on those blobs to get the area and perimeter. With this information, we applied the equation of circularity in order to determine what shape it was. If you go to the next slide. Oh, now, so we basically just showed the camera a piece of paper with different shapes of different colors, just to use trial and error to see what outputs we were getting from that equation. So we knew which outputs corresponded to which shapes. So for us, it would output 1 to 1.9 for circles, other values less than 2 for squares, and other values outside of that range for triangles. we made sure to use ranges instead of hard numbers because obviously in real life, you're not always going to get the same output, and having a range makes sure that it's still able to detect those shapes. And also because of the different angles that the camera is at, then the output would be different because of that as well. So some of the difficulties that we faced were, first of all, mounting the sensor onto the Turtlebot just because we weren't familiar with it. It took us a day, and we had to watch a lot of videos and get the right tools for it. We also encountered challenges just because of the thresholding. We needed to accommodate the thresholding for different lightings and different shades of the same color. So for darker shades, the threshold had to be lower. And also because of the lighting used where we were testing the Turtlebot, those lights were not pure white and they kind of had a yellow tint. So we also had to change the threshold for that. So it just took a lot of trial and error to decide what was the best values to use for the threshold to make sure that it was detecting the colors. There was also a lack of foresight with the Turtlebot and a reduced range. For example, when there's a lot of things in the background, or if the cutouts are too far away, the cutouts are too small in the camera's view, and it kind of gets lost in the background noise as it's detecting every shape and every color that it sees. In order to fix this, we used the Turtlebot in Sanjit's kitchen because it was mostly white there. And so it was able to focus on what we wanted it to focus on. And for non-technical difficulties, obviously it was difficult to communicate due to the lack of face-to-face meetings. And we did want to use the actual Turtlebot instead of a simulation just to have experience with it. And so there was miscommunication when we were passing the Turtlebot to the next person to work on it and explaining the code because you needed the Turtlebot in order to test your own code. And I think that's it. If there's any questions?
Yeah, thank you for the presentation. So you mentioned a lot of things in this project that is pretty great, including the collision avoidance and object detection. So one thing is because the project is about like straight line following. So do you have any like control on this kind of part? So which is the trajectory that you want the robot to control, robot to follow, and what kind of control to put it in?
I'll take that. So for the straight line following algorithm, we basically could not get to it because of the time limits that we had. But we definitely looked into into a centroid. I feel like Taha would know about the centroid, right, Taha?
Yeah, so basically the idea was we'd like try to find the center of the blob and then find the, and then try to try to align the center of the blob with the center of the camera, and then we just move forward from there. And like after like the orientation of the Turtlebot was in the perpendicular direction.
Yep, thank you. Thanks a lot. Any other questions? Any other questions? All right, so if not, that's thanks to the group again for their good job. And then let's move for the next one. All right, so the next one is group 11, and their project is also the fetch robot following a straight line. So feel free to start.
Yep. Lachlan. Hello, Lachlan. Sorry, Lachlan's the one that's presenting first.
Sorry, I had to find my Zoom meeting thing. Hi, so we're doing the Turtlebot Square following as well. Myself, James, and Jason all sort of worked on this project. So just the next slide. So yeah, we followed a straight line based on the square in front of it. There's 3 different squares to be used to determine the to define a sequence following of travel, and the squares will be placed at arbitrary locations. It can be outside the robot's view. It'll find them by turning on the spot. So next slide. So it was done in Gazebo simulation. Due to COVID-19, we couldn't get access to an actual Turtlebot. There's 3 cubes with custom textures. They were made in Blender. And the MATLAB command and control providing the image-based world reconstruction, the structured navigation, and the visual servoing. For getting at for the colors of the cube, sorry, to find the thing, we use Harris corner detection and centroid detection once we're doing visual servoing, and to find the actual cubes, we're using color detection. Yeah, and I believe it's James after that. Oh no, it's still me, I think.
No, it's me.
Oh no, it's James. I lied.
All right. So we have a few main aspects to our project. The first is a image reconstruction and processing of a point cloud, navigation using Pure Pursuit, visual servoing to get to our destination, and we've got a pretty neat GUI. Next slide. Okay, so the first part that we did was an image reconstruction with a point cloud. So the actual Gazebo simulation and Turtlebot actually publishes the ROPS topic, which is already a point cloud, but instead we create our own using the RGB image and the depth image. But first what we do is we color mask out the colors that we want. So if we're looking for the red cube, we'll just use the red points. So to do that, we actually converted it to the HSV color spectrum because it's a whole lot easier to do color masking. We just need to give it a hue and a generous saturation and value range, and it's able to mask out the colors we need. We create a binary image from that where it's just the red pixels are white. And then we combine those with the depth image to create a point cloud of just the red points. So as you can see in the image, there's the red, blue, and green cubes. In the actual processing, we just see the red points or just the blue points or just the green points. We can then find the center of the cube very accurately, just taking the center of all the points. And we can use regression to find the tangent and normal to the actual direction the cube is facing. And from there, we can extrapolate a point 2 meters, 1 meter, and the actual base position itself. Next slide. Jason.
Yep. So once we've got the position from the extrapolation and image reconstruction, we then use that waypoint to essentially feed it into a navigation system. So navigation system, or what we call it wayfinding, is basically a Pure Pursuit algorithm, which pretty much takes the look ahead point as the destination, and then it tunes the angular velocity and the linear velocity based on where it is currently, so the positional error. So it should be going at full speed at all times in the linear direction, and then changes angle based on that. Once it arrives to its destination, it will then turn on the spot using a P controller to face the cube in a straight direction. Once it does this, it will then go into visual servoing mode. In visual servoing mode, it will continuously scan the image frame, collecting the image data, and then it is then color masked and then enhanced using a convolutional kernel to ensure that the detector can work correctly. And then from there, it generates a binary image, which we can use to calculate the image center and the corner features. Sorry, the corner features and then the image center. So it uses a combination of Harris corner detection and centroid calculation. So with the Harris corner detection, it takes that first to determine the center, but if it cannot find a center using that, it just falls back onto the region prop centroid calculation. Once it's done this, it then calculates the error, as shown here in the pink line here, and then feeds the information into a P controller to essentially minimize that error through its angular velocity. So this implementation can also be used to follow another Turtlebot or any other object that's moving as well. So this way we can ensure that it's accurately following an object straight, regardless if it's moving or not. Also, the depth is also used in the P controller to ensure that it follows a particular distance, because in our scope, we said that would be moving towards the cube from 2 meters to 1 meter. And then from there, we would move on to another location. So over here, we have a general program flow and ROS graph, which demonstrates the general program flow and also the general nodes that we have here. So we start off with the program, we scan for targets by turning on the spot. If the targets have been found, we then reconstruct the images and 3D points and generate the travel point. We travel to the waypoint, we wait until it's arrived, and then we go into visual servoing mode. We keep moving in visual servoing mode until it's 1 meter away from the target, and then we go back home. So the depth sensor is the D information coming from the RGBD camera. And you can see that over here in the ROS graph. So Gazebo is where our Turtlebot lives. and then we get all the information, feed it into our MATLAB command and control node, and then that generates an output velocity.
Because we were doing this all in simulation, we thought a GUI was a pretty good idea to allow the user-friendly control of the system, also to allow for changes in the start position, viewing of the Turtlebot's perspective as well as a third-person perspective, and to extrapolate the square location of the actual squares that it detects. So it also had to be non-blocking so that everything else could still run while the GUI was there. We did have a couple of issues, if you want to go to the problem slide, because we talked about that first. So the first few issues we found was Gazebo was new to the team. None of us had really used it before. I think Jason had used it a little bit. So there was a lot of time in setup and trying to understand the documentation and cross-checking to get it so that the robot would run smoothly in there and all of the squares and everything would be in the correct spots. As far as MATLAB performance, we had some issues with MATLAB basically being slow. It's a single-threaded operation, so it's quite slow, and we didn't use GPU power to accelerate the image processing, which led to slow control rates and control errors in the simulation. It also led to issues with the GUI because the frame rate, as you'll probably see later, on the image detection, on the updating images is quite low. It's about 5 frames a second, and that's about as fast as we could get it. Anyway, James will just talk about the problems with the point cloud.
So one of the problems that had us stumped for a while was our point cloud was slightly warped and inaccurate. And the main root cause of this was because I thought the depth image that was being published, each value was the distance from the camera to the point, rather than the distance from the camera to the point along its forward axis. And once we fixed that up, the results were much more accurate and we were able to get to the point very accurately.
Okay, so now we'll go to a live demo. So I'll just quickly swap to my other computer for this. There it is. Okay, can everyone, yep, perfect. So we thought a live demo would be more appropriate because we wanted to show you guys how it can be done dynamically. So currently we've got the GUI here, and we can then control the robot through any means. So we can use the sliders, and that moves forward. We can also set a specific manual position. So we can go to 1, 1, 0, and it will automatically navigate to the position using the Pure Pursuit algorithm, as you can see up here. Sorry, it's a bit slow. Turtlebots are very slow. Yep, and then now what we can do here is we can, so as you can see, the green target is now out of view. So now what we can do is we can scan the environment. It will find these two first and give us an indication of where they are at. And then it will do a rotation around the course in a anti-clockwise direction. So it won't see the greens go to the last point. And as you can see the specific set points where we've set it to move, and it's using the P controller to do that. We decided that PID control is a bit too much for us in the application sense. So we didn't think that we would need the PID control, and it seems, and we managed to get it working pretty well with P control. Okay, that might have been a slight bug there. That should have detected. Okay, either way though. So what we'll do now is we'll just go back to home, and then we'll do a full, just going to red, time permitting. In the meantime, does anyone have any questions?
Yeah, so thanks for the presentation. So any questions?
I was just wondering what made you choose Pure Pursuit, and if you tried any other algorithms.
We decided to choose Pure Pursuit because it seemed to be the fastest way to get to the location. And plus we've had experience with it from programming from X Systems. And what we decided was that Pure Pursuit just seemed to work best for that. And then turning on the spot also produced the sort of best result, because that way it sort of accounts for any type of error that can occur when it's moving, because the physics in Gazebo, sometimes the robot just moves by itself without moving in that particular direction. I'm not sure why, we still haven't figured that out. But that's generally why we use Pure Pursuit.
Originally, it was just a rotate to the point and drive forwards. but we changed it out.
Yeah.
Thanks.
Okay. Oh, wait a minute. There's something wrong here. Wait, that was just lag. So we'll just quickly show the visual surveying part. Okay.
Yeah.
Okay.
So
Yeah, probably
I have one quick question.
Yeah.
So I'm quite I'm quite happy that you're using visual surveying in this project, because you're the only one group during a couple of semesters that which use visual surveying in this project.
Yeah.
I mean, this is what I designed that for. But I mean, as I mentioned, I'm quite open for different solutions. But yeah, so I'm quite happy that you're using visual surveying. One quick question is, because the visual surveying we introduced in the class is a 3D one,
yeah.
right? So how did you convert it into a 2D control, which is 2D velocities?
I'm actually glad you asked that, because I was prepared for that. So with that, we initially went down the path of doing the 6DoF visual surveying, but then obviously it then dawned on us that the visual surveying for 6DoF cannot be applied to the TurtleBot because it only has 2DoF. So essentially what we did was we boiled it down to the basic concept of visual surveying, which is minimizing an error to the point. So then what we did was then we figured out, hey, wait a minute, we can change the angular velocity to essentially get that error down to 0 to move towards that cube.
Oh, that's pretty great. That's pretty great. You're developing yourself the visual surveying algorithm, right? That's great. That's pretty great.
Yeah. And as you saw, I was moving the cube as in the demo. But yeah, that's pretty much it.
Yep. Cool. Thank you very much. So let's move to the next one. The next group is group 4, and the project is also the project is also on TurtleBot, but it's about TurtleBot following each other. Yeah, feel free to start.
All right. Hi. Can everybody hear me?
Yeah, all good. All
right. This is group 4. Our chosen project was the TurtleBot following each other. So next slide is our goals. So our goal for this project was to program a TurtleBot to follow another TurtleBot around a simulated environment. And we did manage to achieve this by splitting this into multiple smaller problems. This included getting the follower to recognize the leader, moving the follower without user input and to follow the leader, moving the leader around the environment, and neither TurtleBot crashing into walls, each other, or obstacles. The next slide are the resources that we used. Even though it was a simulation, we still used quite a variety of resources. This included each of our personal computers, which we installed with Ubuntu 16.04 and Rust Kinetic. This setup was chosen because of the Robotus e-manual instructions. We also used the Python language and libraries, which works well with Rust. The online Robotus e-manual, which helped us learn about, set up, and use the TurtleBot 3 in a simulated environment, which is also called Gazebo, which is a 3D robotic simulator tool that works with Rust and the TurtleBot 3 modders and provides different environments for us to use. Last is the Aruco tag Rust precedence and OpenCV, which we use to solve one of our main problems, getting the follower to recognize and follow the leader. Each of these resources combined led to the success of our project. So next is the approaches that we took. Well, it's a list of our possible approaches to our main problems of getting the follower to recognize the leader and then follow it around. We thought of using MATLAB tools to help track an object on the leader. We thought of using the LiDAR sensors to track the leader. We also thought of using object tracking via color detection of an object, such as a ball, that was attached to the leader. But the approach that we did choose was object tracking through the use of an Aruco tag and OpenCV. After research into each of these approaches, we ultimately decided on the Aruco tag due to its appeal, the many examples and resources that we found online, and because of its success and reliability in other similar projects. So next is our methodology. The main aspects of our chosen approach to the whole problem are listed here. We used 2 TurtleBot simulated waffle models, the Gazebo simulation environment Plaza, which you'll see later, an Iruko tag with pose information, which is attached to the leader model, and a TotalBot control Python file, which controls the follower using subscribed and published information from the TotalBot sensors and the Iruko tag. And then we also use the ROS commands for the user to use and run the program and control the follower robot. The next is visual servoing.
With visual servoing, we use the end effector mounted on the TotalBot, and the detection is through ROCO markers. ROCO markers are pretty much synthetic square markers with black and white borders that determines its ID, black corresponding for 0 and white corresponding for 1. But it doesn't use, it follows an entire 5x5 grid, but only uses the center 3x4 to determine the ID. We were using the ID 0701. RCO's detection was done through its launch file. You can see in the next slide, please, where it's you can follow how the publisher RCO single detects the image and the follower. Can you press the next one, which there should be another image, but I'll quickly share screen to show the image. So as you can see, that's the RCO tag, and you can see the axes. We followed the x-axis and the y-axis for the control, for the linear and angular velocity. And over to Kyle for the rest of the presentation.
You'll have to stop staring at your screen.
Yeah.
Yeah. All right, so for the TotalBot control, we implemented the ROS-P libraries from ROS. So what that allowed us to do was interface with the ROS topics and allow us to subscribe and publish to different ROS topics and nodes. So then we used the twist, ROS twist to subscribe to the ROCO markers and obtain its pose information. So that also allowed us to get the pose information for both the TotalBots, so we could compare how far we want to move each one. And then with the tag information, it displayed us the exact location of the leader TotalBot, giving its X, Y, Z coordinates, its orientation, its angles and velocities. And we also used we created another function that would call this to calculate its distance and then publish its velocities, angular and linear velocities, to the follower TotalBot. So we did encounter a few problems. So obviously with simulations, the ROS kept on crashing frequently, and we had to restart quite a few times the computers and all that, and the code. The rocking motion in the TotalBot, since we added the tag on to the back of the TotalBot, it messed up with the physics of the TotalBot. So the TotalBot kept on rocking, which is still evident in when we show you the video. And the other problem we encountered was when we lose sight, when the follower loses sight of the leader and the tag, it just continues to travel at the velocity it was traveling at last. So we didn't manage to incorporate any stopping if it lost the tag. So this is just a demonstration of what our project was. So here we can we load up all our files. So just loading all the ROS topics and our launch files containing all our Gazebo environment files. So we use the Oroco marker launch file to detect the tag, as you can see on the bottom right, and that will give us our axes that we can visualize, and that's all sent to the pose information in the Oroco markers, and that we can subscribe to that. And as you will see shortly, we would get the Turtlebot to follow the leader. So we just launch our Python file, which has all our control commands to calculate the trajectories. And as you can see, it starts to follow. And if it stops, the robot stops, it stops, and the turning. So is there any questions?
Thanks for the presentation. So any questions? Any questions?
What type of control algorithm do you use to drive the Turtlebot around?
So we just subscribe to the twist linear X, Y, Z and angular topics. Then we just put those into a few variables for the X. So we extracted the X coordinate and the Z coordinate, since those, so the X is for the steering and the Z is for the distance between the Turtlebot. And we just made a simple formula to always maintain that certain distance of 1.3 meters or a little less. And then we just published that information back to the command cmd_velocity message to ROS. So it was a really simple controller to implement. Yeah.
Yeah, so any other questions? Yeah, I have a very quick one. So in your simulation, so you have like some walls in the environment. So
Yes.
do you consider any like collision avoidance during the falling?
Yeah, we did. As soon as it starts to collide, it's just gonna keep going to the wall. But as soon as it regains the sight of the tag of the leader, it will go backwards and reorient itself.
Yeah, sure. So another question is in your demo video, so you only show one with a start, stop, and also turning right. So
Yes.
have you like test any other motions? For example, turning left and also like a reverse or something?
Yes. If you want a live demo, we can give a live demo. I have it ready.
No, that's fine. That's fine.
Yeah. But it works in all. It does it perfectly in all directions. And
okay,
yeah.
cool. That's great. Yeah. All right. So any other questions? So if no, let's thank the group 4 again for that great job and presentation, and let's move to the next one. So the next one is group 6, and the project is also Turtlebot following each other. So feel free to start.
Hi everyone, my name's Sabrina and my group partner is Corey, and we're doing the same project as the previous group, Turtlebot robots following each other. First I've got is the project description, so similar to what all of you guys would have seen in the document that Liang posted. But our target was that the Turtlebot follows the guided Turtlebot moved in the Turtlebot simulation software. And skills that we needed were Linux, ROS, and MATLAB, and then preferable skills would be basic computer vision and control skills. So there were some additional tips that were provided. One was to use the learnt state-of-the-art control algorithm to control the Turtlebot to follow the path of the guider. The next tip was to use depth images and RGB images that can be used to control the Turtlebot. And then finally, it was suggested that we use specially designed artificial markers or patterns that can be positioned on the back of the guided Turtlebot. And this is something we definitely did implement. So we have a quick demonstration for you guys. So hopefully this works within the slideshow. No, it doesn't. So we'll just open it up on YouTube. Okay, so that was the first one. Now we didn't actually quite finish the project. So for the most part, we got the robot moving, but we were still working on getting the visual detection completed. But what we did do is create a video of the visual detection working with a webcam from our computer. So essentially what we want to do, as you just saw in that video that I just played, there was a blue box on the back of the TotalBot. And so this is just some video showing the detection of blue items. So we'll play that as well. So they're just some pens with blue lids that I had, and it's detecting them and just identifying the location of them within the snapshot of the video. So back to the presentation. So we're just going to talk to you about the setup now. So we use three programs to, or three pieces of software to get this working, MATLAB ROS and the Gazebo simulation software. So as you can kind of see in the diagram, ROS was the main program that everything else would communicate through. So MATLAB would talk back and forth through ROS, and the Gazebo simulation software would also talk back and forth with ROS. Now for our code structure breakdown, what we did is we had our main script and then we had a few classes that would complete different tasks. And this was to ensure that we had modularity within our code and it made it easy to edit. So what we're going to do is talk you through each of those scripts that I mentioned in the previous slide in the hierarchy. We're going to walk you through the structure of it and then also some challenges we had completing that section of the project. So this is the structure of the main script. So once we start, we prepare and clear the workspace, and then we complete a ROS shutdown to make sure there are no instances of ROS running within the system. And then ROS is initialized within MATLAB and to set up a ROS connection. And then next we have a prompt that will be displayed within the command window. And this asks the user to run a ROS launch file in a terminal window. And then next, when the ROS launch file is launched, 3 instances of the classes that were written have been launched. So this is just this second last row here. And then we have the ability to control each of those classes. So we'll move on to the next slide. We had 2 main challenges within this component. So the first one was that we found it difficult to get the ROS launch files to launch via MATLAB without extensive background changes. And to solve this problem, we wrote code that prompted the user to run a ROS launch file. And then the second challenge we had is that we found it difficult and time consuming to get our ROS launch file to actually work as well. So this is because MATLAB could not connect the ROS nodes and the TotalBots were not spawning correctly. And we solved this by editing the existing ROS launch file provided in the TotalBot 3 libraries and modifying them for our process and situation. And this ultimately allowed us to save time within the project, and it was a preferred solution when comparing it to creating our own ROS launch file from scratch. So next we'll talk about the robot class. So what this does essentially is create a physical robot within the Gazebo simulator. And so the structure of this code, after the code starts, we subscribe to the ODOM SCAM and CAM ROS topics, and then these classes store the robot specific value in a particular instance. And so following that, the command velocity ROS topic is published and then the class ends. So the actually, I'll go back to this one. So in the motion control class, which we'll talk about next, we use a constructor which requires input parameters and hence requires the ROS topics mentioned of each robot in the Gazebo simulator. And so each of these ROS topics are stored in the class variables. So we had one main challenge for this section of the code. So we found it difficult to work out how to control the robot via the ROS topics. And to be honest, solving this one just required a lot of research and online resources. However, we did eventually identify how to integrate this process in the code, which is a positive. So next we have the motion control class. So this essentially completes all the calculations required to control the robots, and it also sends output values to specific robots that are required to be controlled at any instance. So what we've done to control the guided robot is create a circle function which takes input values from a user and then sends those values over ROS to control the velocity of the specific robot, which is chosen by the user. So you may have noticed in the video that we actually had prompts coming up, and this is because when we were coding this section, we actually found it difficult to kind of, move the robot freely. So we kind of just structured it so that it would go in that circle. And the class also has a stop function, which I'll show you in the structure here. But what it does is broadcast a 0 velocity value to a specific robot, and then that essentially tells it to stop moving. So yeah, as I was explaining, we have the start of the code, and that leads to the constructor, and then the two functions, circle and stop. And that essentially occurs before the class ends. So the main challenge we had with this one was that we found it difficult to control the guided robot and have the follow robot sensing and controlling simultaneously. So to solve this problem, as you may have deciphered from the flowchart, we sent out linear and angular velocities to the guided robot, and the values were static and are changed when the user inputs new linear and angular velocity values. So that in turn changes the motion path of the guider. So next, the visual survey class. So yeah, you would have seen in the video that we didn't quite have the follow robot following, and that's, like I said, because we didn't completely finish this part. But we will describe the progress that we did make, which involves the second video that we showed you. So during the planning stage, what we had decided to do was to have a function within the robot class which would update the image, and then this would take data from the camera ROS topic mentioned in previous slides, and then call on another function that would detect the blue object. So to understand the process on how we would actually detect and focus on an object, we wrote some code that would detect the blue objects from the webcam. So this is the flowchart for that. The slide demonstrates the code we had that conducted the process. So firstly, we get a snapshot of what the camera is viewing, and then we subtract the blue from the grayscale image. Then we filter out the noise and convert the grayscale image to binary. And then finally, the properties of the images are set, and we use this information for the follow robot to detect the guide robot. So in a perfect world, this is what we would have done, but we didn't quite achieve it. So yeah, one of the main challenges is that we found it difficult to find a means of testing without reliable image data from ROS. So yeah, this is pretty much due to the fact that we couldn't get the camera plug-in to work. And so yeah, the webcam code was written to ultimately ensure that the detection code actually did work, and that we could potentially integrate it within our main script. So I've talked about the specifics of the code, but we did have a lot of challenges with the software in general. And we found that learning the software and its capabilities throughout the semester was more complicated than writing the code. So we have 3 challenges here. The first one is that we found it difficult understanding where gazebo files were being pulled from and where to edit the files to suit our needs. And the second one is that we found it difficult and really time consuming to edit the URDF, SCF and Sacro files that would enable a visual marker to appear on the TurtleBot. So essentially understanding file layouts, how we can change them, understanding how the gazebo simulator reads them, were the predominant factors in those challenges, and how we edit the files so that we could use them in multiple instances. So learning about this project really was through the help of Malene, our tutor. So we set up some meetings to ensure that we actually had the correct understanding and knew how to troubleshoot in this area. So challenge 3 is that we found it difficult and time consuming to get the gazebo camera plug-in to work. So we could generate ROS topics and send out data, but where we had the most difficulty was receiving the image data in MATLAB so that we could process it and test our visual server code. So that completes our part of the presentation. If you guys have any questions, feel free to ask them, and Corey will be taking over here for question time.
All right, so thank you for the presentation. Since the time is too long, so we just have one quick question. So if anyone have one quick question. All right, so I have one quick one. So it seems like you haven't finished the visual detection part, but how did you do the video demo at the beginning?
Sorry, how did we do the video demo of the blue pens?
Yep.
Yeah, so we basically just used the webcam input to double check that our code was working. So once we had the visual detection algorithm set and we chose to use the color blue to determine where the follow robot should go, then we just basically used the tools that we had on hand and used our webcam to double check that algorithm.
Okay, cool. Thank you. So thanks for group 6 for their job. And let's move to the next one. So the next one is group 8. And then the project is also about following each other. Yeah, feel free to start.
Hey guys, my name is Reese. I was working on the TurtleBots Following Each Other project with Harrison and Liam. So diving into this project, we had obviously the main aim was to develop a control algorithm that allowed a follower TurtleBot to track a leader TurtleBot at a set distance. But obviously this wasn't enough. We wanted to achieve a certain level of robustness in the system that would allow indefinite following of the leader robot. You wouldn't want it to just follow it for a bit and then it loses it and can't follow it again. And we wanted to go further than that as well, and for it to be able to follow the leader robot in a variety of driver tasks and conditions. So to do this, our scope involved the use of 2 TurtleBots in a simulated environment, and the use of depth and RGB camera data, mainly looking at artificial markers for pose estimation of the leader robot. So our leader control robot was controlled by via keyboard input. So moving this robot around, then we estimated the pose of the leader and fed this into the control algorithm that we developed. So looking at our project methodology, right at the beginning of the project, we aimed to set out clear, achievable milestones. So the first key one was obviously setting up our simulated environment and implementing leader drive control, so being able to control the leader robot with our keyboard. Once we had this done, then we could move on to estimating the leader pose using artificial markers mounted on it. And once we had this, then it was just a matter of feeding the pose estimation into a control algorithm to allow the follower to follow it. So in terms of our project plan, so using these key milestones, we broke it down into low-level deliverables with realistic timelines. This was so that we could delegate branches of code to each team member And the idea was that this progress would be tracked against our WBS and Gantt chart, and then we'd collate the code at the end.
So I was delegated the responsibility of implementing the leader pose estimation component of the project. So from some research, I found a ROS package called AR Track Alva, which utilized unique augmented reality tags similar to some other projects that we've seen today, and the perception endpoint algorithm to determine the relative pose of the AR tags with respect to the camera frame. So I conducted some preliminary testing, which can be seen in the video here, using a simple USB camera and some printed AR tags. We discovered that the package could produce accurate measures of the relative distance and orientation of the tag from the camera. However, in the instance of the single AR tags, the complete tag had to be visible. If the slightest obstruction was present, it would produce null results. Hence, we implemented a tag bundle, which can be seen in the video here, which provided robustness to the program, as now only one full tag needed to be visible to produce results. So after this, my next challenge was to import the AR tag bundle into Gazebo, and as some of the groups have mentioned today, that was a lot more steps than first appears. So using Blender, I was able to generate a virtual A4 piece of paper, and using UV wrapping, loaded the image of the AR tag bundle onto the mesh. From this, I generated a URDF file to load the AR tag into the Gazebo simulation. And then finally, using this virtual AR tag and the launch files I generated from the tag tracking package, I was then able to successfully track the AR tag in the Gazebo environment using the RGB camera on the Turtlebot.
So one of the earlier challenges I faced was figuring out how to drive a single Turtlebot to a set location via MATLAB. This is a bit more complex than I'd first thought due to Gazebo's environment angles ranging from -pi to pi instead of the expected 0 to 2 pi. The solution lay in two steps. First, determining the correct orientation to point the Turtlebot towards the target location, and then second, to drive forward and continually monitor the orientation to make sure you're still moving towards the target within some kind of angle bracket. Another of the earlier challenges we faced was to get two Turtlebots to spawn in the same simulation. On top of that, once we did get both in the same environment, we couldn't control either using the normal Turtlebot teleoperations ROS node. At this point, we weren't overly familiar with the ins and outs of ROS, and it took us quite a while for us to realize that having multiple Turtlebots in the same world meant they advertised to different topics. Simply changing which topics the launch files and ROS node interacted with solved this issue fairly easily. Furthermore, after solving this issue, it was pretty straightforward to get some basic control working through MATLAB. One of the later experiments we undertook was deciding how to move the AR tag around the environment. We attempted to write a plugin that would that would allow us to simply control the AR tag within the Gazebo environment. However, we couldn't get this to work, and so it didn't come to fruition. Instead, we decided to include our AR tag model within the existing Turtlebot WafflePi URDF model by creating a new joint, a static joint, and a new link on top of that. This solution worked well, as we could simply move it around using generic Turtlebot teleoperations launch files.
So finally, having developed the primary core functionalities of the robot, all that was left was to bring it all together into a single program. So as Reese mentioned before, from the beginning, we knew collaborating remotely would be quite difficult. Hence, we made sure that to clearly define the inputs and outputs required for each of our individual contributions to the code. This meant developing a final main loop was quite a simple task. It involved the development of some very minor linking code. For example, using the position of the leader robot from the tracking package and code that I'd developed. A target location was easily calculated using simple trigonometry. And then this target location would then feed into the drive algorithms that had been developed, which allowed the follower Turtlebot to track the position of the leader using a simple proportional controller. In terms of some of the difficulties faced throughout this project, there were quite a few hurdles our group needed to deal with. One of the first issues I identified was in the Gazebo simulation environment. The orientation calculations produced by the AR tag package was less accurate and very noisy, actually to the point that they became unusable in determining the orientation of the leader. However, the position data returned by this package was still sufficiently stable and accurate. So as a result, we utilized the latest two position measurements of the leader robot and interpolated the orientation between these points. This produced a more accurate result than using the orientation from the package, but as it leads into my next point, a noisy position signal was actually generated. We're not sure why. We're suspecting that it was something to do with the lighting situations in the gazebo simulation, but upon running the ROS package in the gazebo simulation, the position signal became a lot more noisy and caused some sporadic position and orientation measurements. To combat this, we tried to implement a Kalman filter to smooth the data a bit of the lead robot, but with project time constraints, we ran out of time to solve this problem with this method. So we implemented a simple data averaging solution, which would average the last 5 position readings of the leader robot, which smoothed the data sufficiently to allow the follower robot to track the leader.
One of the earlier issues we were faced with was that some members' Gazebo applications continually crashed when trying to launch a simulation. Additionally, when Gazebo was working, there were other issues relating to ROS. The solution ended up being simply updating all of our Gazebo applications and ensuring that all necessary ROS package paths were established within the bash RC. This issue was worsened by the fact that we had very little experience when it came to ROS, so we didn't know where to look when it came to solving the issue. This issue was more of an annoyance than a major issue, and it did give us a better understanding of the inner workings of ROS. Another similarly annoying issue was that our simulations ran quite poorly and slowly on some members' computers, most likely due to the fact that Ubuntu was running on a VM. This made it intensely frustrating to work on the project, especially when making minute changes to the code and checking how they affected the simulation. Like the issue of working in isolation that Liam's about to talk about, this issue couldn't really be solved. We just had to persevere and keep working through it.
So lastly, the final issue I'll discuss is related to the difficulties with working remotely. As I'm sure you're all aware, working in physical isolation made collaboration and communication significantly harder. As a team, we agreed upon regular weekly meetings to discuss any issues we were facing and used GitHub to store and track changes to the code we collaborated on. Whilst these strategies eased the difficulty, collaborating remotely was still a significant challenge to us.
So looking back on the project, I think one of the key things we took from it was the steep learning curve we had with ROS, as I'm sure most people had. But moving towards more of the subject learning outcomes, we had a lot of lessons from both sides of the subject, both sensors and control. So working with different types of sensor data and image processing, and then also the development of control loops and algorithms. So I guess that's it. While this video plays, we'll field any questions.
Yes, thanks for the presentation. So any questions? Any questions? Yeah, so I have a very quick one. So it seems like you are using 4 IR markers. So is there any specific reasons why you're using 4?
Yeah, that's right. So as I touched earlier on in the experiments I was doing with the USB camera, so the 4 AR tag markers were loaded into a single thing called a bundle. And so you store the relative position between each of the tags, and it provides more robustness to calculating the, interpolating the pose and the pose of the tags. So when I was having a single AR tag, if any portion of the tag was blocked by any form of obstruction, the whole ROS package would produce null results. But by developing this bundle, you could block up to entirely block up to 3 tags, and it would still produce position and orientation results of the lead robot. So the reason we implemented this was just in terms of in a busy environment, this would provide more robustness. So in case at any point that a tag was blocked, the follower robot could still track the leader.
Yeah, cool, thanks. Any other questions? Any other questions? All right, so if no, let's thank the group 8 again, and let's move to the next one. So the next one is group 9, and which is also working on the turtlebot following each other. So feel free to start. Yeah, feel free to start.
Hi, everyone. My name is Lynn, and my group members are Jen and Jeff. We're group 9, and our project is turtlebots following each other. Our group project consists of 2 turtlebots, 1 leader and 1 follower. The aim of the project is to program the follower to follow the leader. There are requirements that need to be met in order to achieve this goal. These requirements are that the follower has to be autonomous, The movement of the leading bot will be manually controlled by an operator. The follower must follow the leader in any direction it goes, and the follower must maintain a consistent distance from the leader. At the very start of our project, our group set milestones to achieve so that we could finish the project at a reasonable pace. I'm happy to inform you all that our group met most deadlines and completed our project a week early. So how we chose our project. So there are 3 different Turtlebot 3 models: Burger, Waffle, and Waffle Pi. Our group chose a Waffle Pi model as it has a 360 LiDAR and a Raspberry Pi camera. The LiDAR can sense up to 3.5 meters, and the camera can take photos up to 3,280 by 2,464 resolution. So when we began our project, our group tried using VMware, but Gazebo and RVs would crash. We all had to dual boot Ubuntu and follow the demonstrations from Marlene and ran Gazebo, which worked without crashing. So as the subject uses MATLAB, we also chose to use it for our project. For ROS was used as is an open source operating system for robot communication. An important factor is that it provides tools and libraries for building and writing and running code across multiple computers, as we wouldn't collaborate face-to-face during quarantine. So for code version control, our group used GitHub as we're already familiar with it, as it was used in previous subjects. Now Jeff will speak about our approach.
Here's a video of our Turtlebot following the other Turtlebot. The approach we took to achieve this is shown in the flowchart below. There are 2 major decisions that the follower takes in order to do this. The first decision is if the leader is in the field of view of the camera. If it's not in the field of view, it will continuously rotate counterclockwise until it is visible. Once it is visible, it will then calculate an angular velocity to face the leader. The second decision is if the leader is within the range of the follower. If it's not, it will just move forward, but because it's already rotating towards the leader, it will always be heading towards it. Once it is in range, the follower will now calculate a more accurate linear velocity to control and maintain a certain distance from the leader. In the video, the leader is hard-coded. Just an explanation of each section. So the camera, how it detects the leader, we used color as a feature detection. What it does is it detects the color blue. As you can see, our Turtlebot is completely blue. It creates a black and white image. So blue becomes black, and then anything else that's red or green turns white. This makes it a lot more simpler to manipulate the data as it's binary. That way we can find the center of the leader Turtlebot by using the columns of the pixels in the image and averaging the maximum and the minimum column. The LiDAR is also used to determine the distance from the follower to the leader. As I said before, if it's out of range, which is the 3.5 meter distance, it will just move forward. We used a P controller to control the velocity inputs to the follower robot. This was a lot more used once it got closer to the leader, so that it would avoid colliding with the leader when moving forward and maintaining our desired 0.5 meter distance. We would find the distance and angles, but we would have to convert it to velocity. So we use timestamps of the previous scan and the current scan to convert the input velocities. Jen will talk about the issues that we face throughout this process.
Yeah, we did face quite a few issues during this project. I think the biggest challenge was that we faced was just setting up Ubuntu, the Gazebo simulation, and adding a second Turtlebot into the simulation environment. We took a lot of time to set up and prevented us from moving forward in this project, as this was needed to be done first. Another issue was that we initially used the LiDAR sensor to calculate for the angular velocity for the follower robot, we use X and Y coordinates of the leader detected by the LiDAR sensor and use this to calculate for the angle to get the angular velocity. This method gave us an inaccurate angular velocity because the X and Y values had to be averaged. We eliminated this method and used the RGB camera to calculate for the angular velocity instead. This method used the pixels in the image obtained to find the angle between the follower and the leader, which successfully gave us accurate angles and distance to let the follower directly track the leader. Another problem we faced was not being able to control both the turtlebots at the same time, because when we ran the code, the robot just did this. They would only go one at a time. So we solved this issue by running the leader code in one MATLAB window and the follower in a separate MATLAB window, which worked out perfectly. Another challenge was we couldn't accurately rotate the follower to face the leader. The follower kept turning too little or too much. We initially calculated the angular velocity for the follower using the distance between the image center and the center of the leader in the image taken and the time difference between the follower and the leader. We found out that the resolution of the camera of the turtlebot is 3280 by 2464 pixels, but the resolution of the image taken and displayed on MATLAB is 640 by 480 pixels. So we solved this by compressing the camera resolution to match the image taken, then calculate for the pixel length in the image resolution. And from this, we could get the actual distance between the follower and the leader to calculate for the angular velocity. Overall, we had achieved all of our project deliverables and had a great time working on this project. Thank you. Questions?
Thank you. Thank you for the presentations. Any questions? Any questions? All right, so I have a very quick one. So it seems like you initially want to use LiDAR and then it turned to use RGB sensors to do this project. So can I ask, what's your opinion comparing using those two sensors?
So with when we were using the LiDAR, it was very inaccurate because there would be multiple detections of the leader. So by using the camera, we were able to just pinpoint the actual center and just use one marker. That's why we found it difficult with the LiDAR. And also we were trying to head towards a process where we would just kind of use the camera to detect the leader and then use the LiDAR as a sort of collision detection if it was in a full environment with obstacles around it and to create collision detection.
Yeah, cool, thanks. So any other questions? Any other questions? All right, so if no, that's thanks to group 9 again for their project and presentation. All right, so let's move to the next one. So the next one is from group 13, which is about video serving of a handheld camera. All right, so feel free to start.
Hi, so our group was responsible for visual surveying with a monocular camera. So in the group, there was Teresa, Hamish, and myself. Just the next slide. Yep. So from the scope of the project, we had to utilize MATLAB to use visual surveying algorithms to use a video feed and read its destination. The aim of the project is to direct the camera to the desired position by matching the pattern read by the camera sensor with the reference position. Now I'll hand over to Hamish, who is going to go over the methodology of our algorithm.
Hello. So our method of approach for the visual surveying was following the end effector mounted or eye in hand visual surveying model. Due to difficulty getting our hands on a handheld webcam, we had to use our laptop and then move the pattern itself. It still follows the same method though, with the same instructions put out on the screen for the end user. We used a checkerboard to determine the pattern. We started off using Surf, but we had a few issues with that one. We ended up using a detect checkerboard function that was in MATLAB itself to gain our corresponding intersection points. And that's the points that we worked with for the visual servoing. So we used the pinhole camera theory once we had our points, and utilizing the projection chain equations, we developed a function that would estimate the value of the displacement between the camera and the pattern, which tried to account for the possible angles that the board would actually be at as well. And using that estimated value, we put that into the interaction matrix. And then using an error correction of 10%, we then calculated our required velocities and put that out on the display screen, which we just used IM_show on the MATLAB. However, it was not the best. It was fairly slow, probably about 5 frames per second. Yeah, I'll hand it back over to Teresa.
Hi, my name is Teresa. This is the flowchart for our code. It's in 2 main sections. So you can see at the top, it's got the camera intrinsics and the constants. Oh, let me see if I can point at it. Right, so around here are the constants and the parameters. And then below that, from here, is our while loop. And that takes a snapshot from the feed of the video and analyzes the image to obtain the pose of the checkerboard that we use for our pattern. We identify the center of the checkerboard and its 4 corners so that we can match the current pose with the desired pose. And so in this little diagram that we lifted from our code, we show that the corners are named so that this is corner 1, corner 2, corner 3, and corner 4. We use the checkerboard points function to find the checkerboard automatically, thereby, bypassing all the feature detection, extraction, and matching functions. But the rest of our code approach visual servoing almost from first principles, so it's just a lot of calculations from about this point all the way to the end. If I zoom in a little bit, you can probably read some of it, but it's not a fun time. I wonder if I can go next from here. No, okay. Oof. Right, so I've got a video. It's got a bit of a lag, as Hamish mentioned, given the number of calculations that I indicated earlier. This kind of works in our favor as it gives time to move the checkerboard between frames. It's got music as well, so I can't really talk during it. But looking at this image, so this yellow arrow indicates the movement or displacement and the y-axis, and this red one indicates the x and z axis. Okay, let's see. This fuck me dead.
So we didn't get around to displaying the pitch, yaw, and roll on in a more elaborate visual design. So the pitch, roll, and yaw that the camera needs to perform is just outputted as numbers on the left of the screen there next to the yellow arrow.
Is there a part of this video where you show the tilting? I can't remember.
Yeah, about there.
Yeah, skip a little bit then.
So as it's trying to, oh yeah, gone past it.
Okay.
As it's trying to achieve the position in front of the board, some of those directions appear to be a little bit bigger than they require, but you got to, for that specific example, it was trying to achieve 500 millimeters in front of the board.
Oh.
And so this is just a few of the outputs. So we're tracking the outputs that it was trying to produce in the top left of the screen there. That is the outputted velocities that the control is trying to direct the camera in. And the bottom left is the angles that the control is trying to tell the camera to move in. And on the right there, tried to set up a simulation for the actual visual servoing, but I couldn't get around to finishing it. I think I messed up a few of my equations when making a simulation of it, and it's a dead offset, as you can see. So the red frame in that little simulation, the upside down U is the initial pose of the board. The blue is the pose that we are trying to achieve, and the yellow is the current pose. And those lines in between are it tracking. Yeah, next.
So the ideal application for monocular cameras for visual servoing, it's ideal when the sensor depth is not an issue. Also, the pattern needs to be fixed or have little to no variation and doesn't need highly accurate results. So this could include object tracking from drones such as a car, or possibly pick and drop applications. Yeah, I think that's it. So thank you. Is there any questions at all?
Thank you for the presentation. So any questions? Yeah, so I have quick two. So the first one is, it seems like when you show the left demos, it's sometimes the right, I suppose the right arrow is the control direction. I mean, is the linear velocity which pointing to, right? So sometimes it suddenly changed to a different direction. Do you know how it happened?
Yeah, I think sometimes it's my hand going in front of the pattern, which makes the camera detect like a slight variation in the pattern or a different angle or something along those lines. It would normally correlate with a variation in the detected pattern.
Yeah, sure. That's not a big issue. So another question is, have you tried that based on the control it reported from the video serving? You try to move the camera and to make it the trackboard moving into the desired position. Have you passed that?
I think I did. I used that code on my laptop, and I was moving my laptop around. And it was still working fine. So.
Okay, cool.
Yep.
Cool. Thank you.
It's a bit difficult because you're in the frame of the laptop.
Yeah.
Oh, yeah. I mean, it's quite difficult to do the validation for the real case. I mean, that is the one of the thing in my mind we can do that. Yeah, sure. So any other questions? All right. So if no, let's thanks the group again for their great job. Then let's move to the very last two. So for the very last two, they are personalized projects proposed by the groups. Then the first one is from, is about video serving of the camera on the DJI Tele, which is from group one. So feel free to start.
Hey guys, this is Daya. I'm doing visual surveillance on with camera on a DJI Tele drone. It's essentially the project is like a proof of concept that it is possible that a DJI Tele drone can be used as a selfie drone. That's the drone will be flying around. It will be directing the camera to someone, and when that person moves, the drone will follow by itself automatically. You don't need to use a controller or anything. So the project is carried out in the following order. So first, you have a camera on the DJI Tele drone, which needs to be calibrated because I did not know the focal length and all the intrinsic parameters. So I printed out a calibration checkerboard, and I used what we did earlier in the semester, camera calibration, to get the intrinsic parameters. So I got the focal length, the principal points of the camera on the Tele drone. And after getting the parameters, I have to get the object detection algorithm. So I did not use the SURF features and the Harris corner detection because I want something more robust, something that aligns with the project, the purpose of the project. So what I did was I used Viola-Jones face detection algorithm. So that detects the face of a person. People's faces are quite unique. So you have the eyes and up like noses and everything. So what the algorithm does is it like classifies the features and it detects the face. So after detecting the face, I get a bounding box. So I use that bounding box, the coordinates of the bounding box to Visual Server, just like what you would usually do in a visual surveying project. And I get the control velocities, and those control velocities are the idea is to interface those control velocity back to the drone, but due to difficulties connecting drone and MATLAB, that did not run very well, but I do have some results on that. And afterwards, you control the drone from MATLAB. So that's the general outline of the project. So the first, after camera calibration, the very first important step is to get the object detection algorithm. So what I did is the Viola-Jones algorithm. The convenient thing about MATLAB is you have this computer vision toolbox, and that computer vision toolbox, you have this cascade object detector. So in that detector uses Viola-Jones algorithm to detect objects. What you can do with that detector is that you can actually train different objects. Say if you want to detect an apple or like a teddy bear, you can train those different images, and you can get a detector up and running. So what I did is I use my face as a classification image. It's gonna work pretty much with any face. So in the figure, you can see a green box, right? So that green box is the output. So it's it's the output from the vision.cascade object detector. So what it does is it detects a face in a frame, and it outputs a bounding box. So the coordinates of the bounding box, and those coordinates are used to draw that little rectangle. So the good thing about this algorithm is it results in pretty similar type of information from like the SURF features and Harris corner detector. You get a bounding box as a result, so which is pretty versatile to work with. So afterwards, you get after you get the bounding box for the face, you go to visual surveying, which is I just used the pinhole camera method, which is which is what we learn throughout the semester. So the intrinsic parameters from the calibration, the depth value, however, is obtained through extrapolation. So what I did was I took different frames of me, and at different distances from the camera, and the width of the bounding box is calculated and is extrapolated so that the Z value is not set constant, the Z value is always changing so that it matches the actual value. So the image Jacobian is calculated using that derived value that is just calculated, and the algorithm is loop. So yeah, so what the visual sovereign algorithm gives is the control velocity. So those control velocities have to be like we have to do something with the control velocity, right? So what I did with the control velocity is I used those control velocities as a reference, and they're sent to the drone. So interfacing the drone and MATLAB is kind of straightforward in this case because MATLAB the latest version of MATLAB, R2020A, has this support package for DJI Teledrones, which is why I chose the drone in the first place. So MATLAB has this support package, and the good thing is like it's not very complex. It's not like you don't need to do a lot of like connection between them. It's just, and you have to like just connect it through Wi-Fi and you get a connection between drone and MATLAB. The bad thing is about this support package is that when you like do flight commands, I'll show you that in the video in a sec. So when you do flight commands, the code is blocked, so it's not multi-threaded. So when the drone is moving, you can't do any further calculations. So that's not very versatile like in the project. So as you can see here, the drone has a different coordinate system to the image coordinate system we use in visual surveying. So that has to be transformed, which is not the biggest deal here. So what we can do with the drone is we can translate and rotate. We can take off land with MATLAB as well. So yeah, so that's the drone, and we're gonna have a look at the video. So this is the main code. So one a quick thing about the main code I developed though. So in the main code, I have two modes. So the first mode is using the webcam. So if you don't have the drone, you can still use my code to test the visual surveying algorithm and face detection algorithm using the webcam that's available on the laptop. The second mode is the drone. So here, I'm just going to show the drone mode. So at start, the drone will take off, and what it's going to do is the drone will keep rotating until it finds a face. Okay, right, so the drone will find the target. It's quite slow when the drone is operating because of the blocking mechanism of the movements. So what it's going to do is the drone is going to find the face. As you can see in the frame here, the drone is going to find the face, and the blue box in the middle is the target where we want the face to be. So the drone is going to get the face in the green bounding box, and the velocities over there, Vx, Y, and Z, are the velocity with which the drone should move. And you have those camera commands down there, 1, 2, 3, that says move camera towards the object, move camera towards left, move camera up. So they essentially say where the drone should move in order to match the green box to the blue box so that the target is fixed in the center of the image. And hold up, yeah. So one of the failures is that with the MATLAB support package, we can't send the control velocities directly to the drone. What we can do is we can move the drone by displacement. So what I did for demonstration purposes was just moving the drone like in XYZ direction. For if the control velocity calculated is higher than a certain threshold, the drone will move in that respective direction by 0.25 meters. So in this video, you can kind of see the drone will try to move along so that my face is center in the image. Yep, so that's actually about it for the demonstration. And for the further improvement, the MATLAB support package, even though it works really seamlessly, it's not ideal because of the problem I mentioned. So there's a Python script actually. So if I can somehow get the Python script up and running, I would have a better control over the drone, like the actual velocities, so that the drone will actually have a very versatile movement. And for object detection, the result is just a bounding box. So if we could somehow get better object detection models, the drone can actually rotate around and follow the face in real time. So yep, that's about it for the project. Do you have any questions?
Yep, thank you for the presentation. So I have a very quick question. So you mentioned you use MATLAB and also you use Wi-Fi to do the communication between your laptop and the drone. Yep. So do you find any delay during this communication?
Yes, there is around whenever I send a command from MATLAB to the drone, there's around 3 to 5 seconds delay.
Oh, 3 to 5 seconds delay.
Yes.
So is there any way to make it shorter? Because 3 to 5 seconds is quite long, right?
Yes, exactly. So with MATLAB, I don't see any improvements if I'm gonna do it with MATLAB, but I've seen some other people doing similar projects with without MATLAB on their own Python script, so that runs a lot faster.
Yeah, cool. So any other questions? Any other questions? All right. So if no, let's thank the group again for his project and the presentation, and let's move to the very last one. So the very last project is about the video serving of the UR3 by using Kinect. So feel free to start. Thanks.
Hi guys, everyone hear me?
Yeah, all good.
Okay. So we did a UR3 3D scanner with a Kinect on the end effector. This was done in Gazebo. Next slide, if possible. The way that it worked, that we needed to find the position of the end effector or the camera in space. So what we did, we used a QR code to determine the global position. But then we use that to find the object location using IVBS, and then eventually our resolve motion rate control to image the sides of it. On the right, you can see a flowchart of the way that simulation works. So we had a GUI which called the scripts, and we also had a MATLAB simulation in there to make sure that it would work. Then it interfaced with ROS through VPN. So we had Gazebo running on a single computer that we could all connect to through this VPN to send, push and receive data and commands, which then would control the UR3 for the collecting point cloud data and such.
Cool. So the first step that we needed to do was to identify the camera's location in the 3D world, so or in the real world. So if you were to be holding a camera, for example, we needed to know where that exactly would be. So here we're using a QR code, and to achieve this, the camera takes a snapshot of the QR code. We convert this image into black and white to try and get rid of any other issues in the image. We do some canny edge detection and run some BW boundaries on there. So as you can see with the red lines around the QR code, we're able to detect the markers there. And that's because they're pretty unique in the environment. They've got 6 rings around them, both on the inside and outside of the white lines there. So doing some further analysis, we could identify which is the top left, top right, bottom left, and we're able to get the camera's pose in the environment. So here's a bit of an image there, so we can see where the camera is relative to the QR code there by using this information here. So we then next step needed to obtain the location of the objects in the environment. So here we've got Baby Yoda in the Gazebo environment. What we're doing here is we're taking the RGB image and sampling that to be able to identify the object, its centroid, width and height, as well as the Z depth data. And from there, we're using similar triangles and our knowledge of the pinhole camera view to determine the object's location in the local camera coordinate frame. Then we're using forward kinematics to apply this to the global frame as well.
So the object scanning path trajectory utilized both image-based visual servoing and resolved motion rate control. IBVS was used to locate and maneuver the camera position to above the object, while RMRC would position the camera to view the sides of the object. To simplify the points which the IBVS controller was locating, the desired object was expressed as a bounding box. Using the top 4 vertices of this bounding box as points which the controller looked for, the camera was moved to the top of the object and looked downwards. Initially, the controller would use a small lambda value of 0.2 to ensure the arm didn't become unstable initially when correcting the error between the actual and desired points. However, as the error approached 0, the speed of the end effector would slow down dramatically. To avoid this, lambda was increased to 0.9 when the error had been reduced, and a high lambda value wouldn't cause the arm to go unstable anymore. As mentioned just before, the RMRC controller would move the camera to positions where it could view sides of the object. First, the controller would determine the task-based Cartesian trajectory between the current position and the desired position by interpolation following a trapezoidal velocity profile. From this trajectory task space, velocities could then be found. In order to control the robot, the unknown sequence of joint velocities was then required. The inverse Jacobian enabled mapping between the interpolated task-based velocities and the required joint velocities. Despite this control method providing real-time and precise end effector motion, it came at the expense of singularities arising. This was managed by optimizing the inverse Jacobian by using damped least squares to dampen joint velocities as a singularity was approached. So collision detection also used bounding boxes to simplify the links of the UR3. By checking points in the environment, if they had entered the bounding boxes, the controller would be signaled that an obstacle collision was imminent and movement was halted. For self-collision detection, links 4, 5, and 6 of the UR3 were expressed as point clouds and checked to see if they had entered the same bounding boxes used in the obstacle collision. And if one of these points had entered, then a self-collision was known to occur.
So finally, while we're doing the motion rate control, we were collecting point cloud data to stitch up using SLAM. So the method that we used was the iterative point cloud registration method, or ICP. It was picked because it's the least resource intensive and fastest. So the way it works is that the data that you collect, you downsample it to an appropriate level, and then you pair them off and you times transform from the first one to the second for the whole data set. And then once you've done all that, then you multiply it to the initial transform from the very first stitch that you take. Unfortunately, our simulation didn't stitch very well. As you can see here, we have multiple radiators. That wasn't supposed to happen. We believe this is because there wasn't enough sort of other objects in the simulation, so there wasn't enough points of interest for it to get an accurate stitch. So that may have fixed the issue that we were having. Another way would have been to use a different SLAM algorithm. I did try to use RTMAP within ROS, but unfortunately I was unable to get it working on my laptop. So we stuck with ICP to try and get it working as best we could. And yeah, that's where we got to. So yeah, any questions?
Cool, thank you for the presentation. So I have two questions. First one is, one question, one suggestion. So first one is, sorry, the first one is, do you have to do the hand-eye calibration in your case?
Yes, we did. So I found a like a checkerboard where we could set the checkerboard, like how many, the parameters of it, and import it into Gazebo to get like the focal plane and the focal distance and that kind of thing. So we did have to do that.
It's fine. So okay. So the next one maybe some suggestions. So if you use ICP to register the point cloud together, because you have the positive net and effector, you can get it from straightforward kinematics. You can directly read it from the robot, and also if you have the hand-eye calibration, then you have the pose of the camera. Then in this case, you can make it as the initial guess of the ICP, and I think that pose is good enough to make ICP converge. So that is one suggestion I made. The other one is if you want to do this kind of like the point cloud registration or like reconstruction from the RGBD sensors, then there are some more public available codes that you can try. So one is called Kinect Fusion, and the other is called Continuous. So both of the two, I think it will work quite well in your case.
Thank you for that.
No worries. So any other questions? Any other questions? All right. So if no, let's thank the last group again for the presentation. All right. So I'd like to thank you all for this presentation. So it's the presentation day is always the most excited day in our subject, and in this semester it is unexpected that it is quite well organized, even with it online. So during the last couple of semesters, we always have some issues during the presentation, but we don't have any issues happen in today. So that is pretty great. And I'd like to make some conclusions or some summaries about the presentation. Maybe we can, it will be helpful for you in the future. So the first one is, I think most of you have a better feeling about the presentation, right? So in most of the cases, the presentation is always the best way to present your work, And it is not only in the engineering, it is not only in the mechanics, this is the case for everywhere. So for anything, for everywhere. All right, so how to present to the others with a limited time and to let others to be impressed by your work, that is the most important thing, and presentation is the best way. I think all of you, I think after this presentation, then you have a better feeling about this, right? And some suggestions about the presentation. So you may do some presentation in your future. So in your future career, you want to present your work. So you may do some presentation in the future. So some comments or suggestions. So the first one is about timing. So timing is really, really important. So in this, in today's presentation, so I got a couple of groups. So their time is more than 8 minutes. But the good thing is most of the groups, they are within 10 or 11 minutes. So it's not that like that long. But the thing is, you know, for some presentations, you may not have the chance to continue presenting your work after the limited time. And if that happened, it will be a very horrible experience to you, because you have lots of things that you have something that you do have chance to present to the others, and then you are stopped by the chair. So that is a very horrible experience. So I didn't make that because I do want that horrible experience to make the horrible experience to you, but it may definitely happen in other cases if you have presentations later. So timing is quite important because they have the limited time, which means they have so always that will be quite short, which means they want you to present your work in a very short time, but not make others like sleep, right? So the others will have will be concentrated on your presentation and will get the most important information within a very, very short time. The timing is quite important. And another thing is, I think it's pretty good that a lot of groups they mention their problems and challenges during the project. But what I want to mention, I think I mentioned that before, but what I want to mention is that the problem or challenges is not the most important thing in your presentation. So I'm going to upload this video to the UTS Online, then you can see the record of your presentation. So you can have a feeling that after you introduce everything, so which part the others can consider as quite important. So for example, if you have 8 minutes presentation, your most important thing is about your work. So what's the purpose of doing that? What's the methodology, and what's the experiments, and what's the left demo, what you achieved, right? So the problems and the challenges, they are not the most important thing in this presentation. So which means if you use more than 1 or 2 minutes to present that, there will be not positive feedback on that. But the thing is, having the problems, challenges, they are good. If you can manage it within a very short time, then which means it will show the others the information that you really did the work. You really did work. It will show you will show the others that your work. So how much work you've done, right? But what I mean is within a very limited time, because that is not the most important thing in your presentation. All right. So another thing is, I think it is pretty good in this year that no one is showing the code and spend too much time on the code during the presentation. So I do have it in the last couple of semesters. So showing the code is not that meaningful, because even in this case you only have 8 minutes, right? So it's better to give a summary. It's better to make a summary of your project, and also summary of the methodology and summary of the experiments. But if you want to go to that detailed, the thing is that they may not. The audience may not have time to listen to that, and also it may make the audience that a little bit sleepy because they may not quite familiar with your code. All right, so try to introduce your work in a way that which is a summarize of your work or your methodology, not a very detailed code. So I find most of the groups, they show the structures of the group. That is pretty great. So don't need to go to very detailed about each of the components and of the work of the code, but it's better to have a general flow chart or general figure that's showing showing your code of work, and that is fine. All right. So another thing is, I think you have a better feeling as well. So the audience will not be too much on the words. So if you have some slides with purely words, a lot of words on that may be not a good idea. So it is better to make your slides with few words, bullet points, and also some figures and some videos that the audience will. After the audience look at the figures and the videos, they will definitely know what you're talking about. Right, that is a better way about presenting it in your slides. And Another thing is about the balancing of the works. The balancing of the works you are presenting in your presentation. So in this presentation, you have 8 minutes to present, right? So for some of the cases, if they only want to do a teaser presentation and they may ask you questions later, they may be even like shorter. So I have some presentations with only 3 minutes. So in this case, it needs to somehow balance the methodology that in your part together with the introduction and the experiments, right? So if you just use a very little bit time on the methodology, then the others may think you didn't do too much work, right? But if you use too much time on the methodology, then you don't have time to show the others about the demo or the experiment, right? So that is some kind of like balancing. So before you design your presentation, so you need to think about that. And the very last thing I think I mentioned a couple of times is about during the presentation. The most efficient way to persuade the others is about the live demo, right? So I think you have better feeling after this presentation day. Then if the others showing you some live demos or video demos that it finished the work, it finished the task in the project, and you trust it, right? So that's the most easiest and most efficient way to persuade the others. All right, so that's some conclusions or some kind of like suggestions for the presentation. Then I guess it may be helpful for you in your future career. All right, then let's go back to this subject. Today is the very last lecture of this subject. I'm really sorry to say that, but this coming to the end, right? So I would like to use this opportunity to thank you all for all your support during this semester, because this semester is so special, it's so different. So we move everything online. So I do apologize that I didn't make the subject in this semester with the maximum experience of the sensors and the robots, because in the previous semesters we do have like hand activities which you can play with real sensors, and also in the group projects, and you have the chance to work with real robots in the previous semesters. And also we find we have a lot of like live demos then they can do during the presentation by using the real robots. But I'm really sorry in this semester that you can't do that. You can't maximize this kind of experience with real sensors and robots. But what we try to do is we tried a lot to set up with the simulators, with the sensors and the robots, and also we log some real data sets from the sensor that you can play with. So I mean, I'd like to say thank you all just for all your support for this very special semester. Thank you so much. And another thing is I want to say is if in your future career, suppose you are doing engineering in this area, so in the mechanical mechatronics or robotics, or any other area which is related to engineering. So if you have the chance that in your project you lead it or you participate in, so you use any of the thing you learned in this subject. For example, what kind of sensor you want to choose, or what kind of like control you want to use, and how you can like manage the project, divide the whole project into different small aspects, small problems, and solve it separately by using some kind of like method or public available library or codes. So if any of the things you learned in this subject that you may be used in your future career, I will be really happy. And even you are not doing engineering anymore, but maybe you need to do some presentation in your future career, and you have a better feeling about what is a very good presentation, and you design it following that kind of idea, and maybe it may help you to in your future career about presentation, and that's that thing I will also be very, very happy. All right, so the very last thing is, although this is the very end of the lecture in this semester, this is not the end of this subject. This is not the end of this subject, I want to mention. So the first thing is, please return the peer review form to me via email and with your names as well. All right, so your marks on the presentation will purely based on that, and please email it back to me. All right, so please email it back to me. And the next thing is about the report. The next thing is about the report. So the deadline of the report is tomorrow. You can send me anytime. So it doesn't have to be the close of business time. Then you can send me anytime tomorrow. So I think most of you have finished the project, and you don't have to do too much on the improvement of the project. So I believe a day and a half will be enough for you to write up the report. And as I mentioned before, so the report, you need to submit it individually. So each student needs to submit your final report. And the final report is a complete final report. It is different from the mid-review report. In mid-review report, you just need to write the things done by yourself. But the final report is a complete final report for your project. So which means you need to write it up with others' works, but you need to write it up by yourself. All right. And in the previous semesters, if some of the groups, they promised to show me some lab demos to improve their lab demos with robots to improve their marks, and I gave them a couple of days extension on the report. But in this semester, I believe this is not the case, right? So you don't have to work on the demo on the real robot. So which means I believe that a day and a half is okay for you to write up the final report. All right, and the very last thing is about the final exam. We still have final exam, but it's not that much. It's only 30%, and please do a very good preparation on that. And the good thing is it is open book project, so you can use any of the materials from the lecture notes, and also you can use MATLAB or any coding method to check your result. But the thing is, you can't directly put the code on it. I need to answer that, and you can use the MATLAB or other coding methods to check your result. All right, and I also manage 3 consultation time, and I've sent it via the announcement in UTS Online. So 2 are in the morning, which is the same time, in the morning, and the third one is in the afternoon. All right, so in the next 2 weeks. So so if you have some questions during the reviews or preparation of the final exam, so please join the translation time, and we can discuss together. And also if you have time, so if the time is not suitable for you, so just simply send me an email, then I will organize other times, then we can have translation together. All right, so I think I got some other questions. For the final exam, so this year the final exam is a bit different from previous years. So I need to redesign a lot of things. So which means it may not be that with practical questions. So in the previous semesters, the quiz 2 will be some kind of like practice questions for the final exam. But in this year, they will be even a little bit different. So my suggestion is you go through every questions in quiz 1 and quiz 2, but it will not be happened for the camera calibration. So it will not be happened with that. But go through with other questions in quiz 1 and quiz 2, and go through every single practice and also activities in the lecture. All right, and some other questions. Yeah, so if you can send me the report anytime before tomorrow 10 a.m. and that is fine as well. All right, so before tomorrow, sorry, Wednesday, tomorrow is Wednesday, before Thursday 10 a.m. that is totally fine. All right, so anytime anytime tomorrow you send it to me, that is fine. And some other questions. Yes, so for the flowcharts and pictures, you can share it, but don't copy the report. Don't copy the report. All right. Yeah, so there's no limitation on the final report. My suggestion is put as detailed as possible about the things you've done in the project, but don't copy and paste code in it. Do not copy and paste code in it because you've submitted code already. Yeah. I can't say what kind of things you need to focus. You need to focus on the final exam. There will be no coding, definitely. There will be no coding, definitely. But there will be definitely like long answer questions that you need to write down the necessary equations, and you may need the MATLAB or other like coding softwares that you do some calculations. All right, so there will be short answer questions and long answer questions, and including the calculations, something like that. I'm trying to make it like different students will calculate different things, or different students will get different results for the calculations. I'm trying to do that, but not 100% sure if it will 100% work. Yep. All right, so any other questions? Any other questions? All right, so if no, I'd like to thank you all again for all your great, sorry, another one. Can we put screenshots onto the report? Okay, so you can put screenshots, but my suggestion is you only put pictures with necessary pictures. Screenshot of the code, better not. Do not. It is good to put the structure flowchart of the code, but better not to put any single things about the code. All right, so you submit the code already. So you can describe the code by using a flowchart. Then, but not put any code onto the report. All right. So
Liang, could I quickly just give a couple of closing remarks?
Yeah, sure. Go ahead.
Yeah, I just wanted to say, like, I know that everything was probably much more difficult than usual in terms of managing your projects, and even your presentations. Doing it over Zoom is a strange and difficult thing compared to a regular presentation. But despite all of that, I thought most of you guys did a really good job. And just to echo what Liang said about your presentations, especially when you are pointing out your challenges, just make sure in the future that you try to not sound like you're giving excuses for not achieving certain targets and goals, and maybe phrase it so it sounds more like sort of like challenges that you have to that would be helpful for maybe others to proceed forward, or basically issues that you think could be improved, rather than making it sound like excuses. Having said that, I thought most of you guys did a really good job with your presentations, and in terms of the presentation skills, I wasn't bored at all, because I like usually listening to like a Zoom meeting for about 2 hours at a stretch is a very boring thing, but I was engaged throughout the whole period. So just want to say thank you for also bearing with us during this difficult time. Especially most of you contacted me for one-on-one meetings, which was great. And I apologize if some of them were rushed, because at certain times I had to talk to about 4 or 5 groups, and I only had a very limited time to talk to all of you. So thank you for bearing with us with all that. And still, I think despite all of that, most of you did a really good job with your projects, up to, I mean, the standards of previous semesters as well. So good job, and I hope you guys had fun through this whole thing, and good luck for the exams.
Thank you, Marlene. So as Marlene said, so all of you have done a really good job on this subject and also the project as well. And we would like to thank you all for your support during this hot semester. Thank you all so much. So and again, this is not the end of this subject. And even as the end of the subject, if you have any questions about the related topic, and in your future career or in other subjects, you just feel free to contact us, and we will try our best to solve the problems you ask. All right, so thank you all for the whole semester, and good luck for your fun exam. All right, thank you. See you guys. See you.